I work at University of Warwick with Liz Wellington, and I'm part of the PCT team, but linked to the Res Farm project, just to give you context. So I'm going to present the first half of this talk, and it will be on the... Sorry, I've just got a message about the recording in front of my slide. Apologies, so I'll try and get rid of that. Got it. So it will be the introduction to geographic information systems, otherwise known as GIS, and then I'll pass over to Mads for more statistical analysis. So my talk is going to be a brief look at what exactly is GIS, and then to talk you through the different levels of building a GIS map. So we'll look briefly at layers, adding data, vector data and raster data. I'm going to use a site which we're studying in the Res Farm project in India as my example for building this GIS map, and the visuals will all be looking at a package called ArcMap. And then finally, time allowing, I will present some data on the Thames catchment. So that's a river in the UK which has already been completed, and that's also looking at antibiotics in the riverine environment using mapping. So what is Geographic Information System, or GIS? So it's a very powerful system which does multiple things, but essentially allows you to connect data, georeference data, with a map. So it allows visualization of spatial data, but more than that, it allows you then to go on to look at patterns and relationships between those data in spatial context. And also you can look at it over time as well, so look at either trends or different distinct time points. So it allows you to understand the geographic context of your data. And then once you've done all your analysis, the other thing it's very good at is improving the communication of those results through very polished maps which are specific to your purposes. So it's very powerful and many different aspects to it. So another way of thinking about what geographic information systems do, so it's centered around your digital data, and it always needs a georeference, typically XY coordinates, but it can also have Z. So XY would maybe be your latitude, longitude. There are a variety of different coordinate systems which can be used. So it allows you to capture data, create data, display data, analyze data, manage your data, because behind your within your GIS system, behind your maps, are geodatabases, and so your data can be linked in the same way as in any database. You can link tables, so once you're doing sampling and you're doing multiple different analyses, you would have one table, for instance, with your sampling data, and then multiple tables with your analytical data, which would then be linked, and you can access all of that through your mapping suite. You can store data and check data, and your typical outcomes, your maps and your statistics as well. So there are actually quite a large number of software packages. Some of them are quite general and some of them are really quite specific. Two of the main ones that are used are ArcGIS, and that's a comprehensive package. It's a software suite, and you can access that either online or a desktop version, which is the one which I use. The downsides to using ArcGIS, which is a very comprehensive and user-friendly package, is that it does need a license. So University of Warwick has a license for the desktop version, which is why I use it. The desktop version has limitations in that it's Windows only, so it won't operate on the native operating system of a Mac OS. So I currently won't run it on a virtual machine, but that's not actually going to be possible for long. So there are some limitations. There are other alternatives as well, and one of the main ones is an open source software and free called QGIS. I think that's Quantum GIS, and I think it's quite a similar package and with very similar functionality, and that operates on Windows, Mac OS, Linux and Android, so there are advantages to that as well. I'm going to be showing images using the ArcGIS, but you can achieve similar results with other packages as well. So the ArcGIS desktop is a suite of software, and the packages are all integrated together. There are a number of different elements, but the key elements that, certainly the ones that I use particularly, are the ArcMap, where you're drawing your maps, adding your layers and adding your data and looking at the statistics. But behind that, the ArcCatalog stores your geodatabases, and that's where you would do your linkages and uploading your data and making sure that the georeferences are all included, etc. So on ArcMap, your maps are drawn in sequential layers using the data that you have stored in your ArcCatalog, and that's the next steps that I'm going to just go through in brief. So to introduce the area that I'm going to use to demonstrate the map drawing, it's a town called Bardi, which is an industrial town in the most northern area of India, Himachal Pradesh, and it's in the district of Solan within there. So just to zoom in on Himachal Pradesh, and you can see Bardi here, and the area we're going to be looking at in particular in these maps is the one in red. So the first thing that I'd like to show you is that the maps are built up in layers, and the layers that you can visualize on your map are shown on the left hand side of the ArcMap. I should say these are all screenshots from ArcMap. I've deliberately not shown you the polished reports that you might have at the end, because actually I think it's more useful to show you screenshots of the process. So there, I actually have a number of layers here, but I'll briefly say how you can add extra layers. The only one that's visible at the minute is the one with the tick here, and that's how you decide which layers are visible. And I currently have a base map, so a world topographic map, which you can download from online. And so you can see on here your typical features of rivers, district boundaries. This is the town of Bardi here. You can see also such things as this is a forested area, etc. And then if you do want to add data, then there are a number of different ways of doing this. So one is through this plus button up here, which has a drop down menu, and you can add data, either your own data, which if it has an XY coordinates through there, and you can also add from online, so that actually through ArcGIS, and I understand through QGIS as well, there is a huge online repository of data, and as with anything you get online, you do have to quality check it. A lot of it's open source, which is a fantastic resource, but you might need to quality check and tweak it appropriately, but it's a good starting point. And the other place for looking at data is the ArcCatalog on the right of my screen here. So you can access it either through the right of here, and you have a sort of I haven't got a visual of it, but a column at the right where you have, it looks very much like your Finder window, or you can open, if you want to do more detailed manipulations of your geodatabase, you might want to open the ArcCatalog program itself. So I'm going to talk through adding a few different sorts of data type. The main two types of data type are either vector, which is your coordinate based data type. So that's typically XY, but you might have an altitude, a Z factor as well. And as I mentioned earlier, there are different coordinate systems, and you have to make sure that your data is linked up with the appropriate coordinate system. For instance, if it's latitude, longitude, you would link it up as that. And within vector data, you have three main types. You have your point, so your individual XY data. You have your line, sometimes in ArcGIS called a polyline, which is a sequence of individual points which are linked together. And then you have your polygon, which is effectively a polyline where your beginning and end vector coordinates are the same, so you make a shape. In ArcGIS, and I think QGIS as well, the files that contain these data are all called shape files. The second sort of data type, which I'm not going to go into in much detail, but you need to be aware of, is raster data. And this is a matrix of cells, or pixels if you like, across your geographical space, arranged in columns and rows. And each of those small areas, the size of which can vary depending on your raster, reflects quality. So it could be, for instance, the digital elevation model, which we talked about in the first talk on Monday, is an example of a raster. And so you might have different heights which on your map are represented in different colours, for instance. Other examples are things such as weather data, so rainfall might be represented as a raster. Land use can be, or it can be reflected as polygons. So moving on to actually showing you adding some layers. First, I'm going to look at a couple of examples of points. You can see over here that another layer has been ticked, and just one dot to begin with to show you, and this is of relevance to AMR. One of the things that we're looking at in the ResFarm project is the impact of the common effluent treatment plant in Bardi on the river, so we'd be looking upstream and downstream of that. And so that treatment plant has been plotted here, and you can label your points. You can also change your symbols. All of these things are accessed through right-clicking on the name of your layer in your layers sheet, or for the symbols you can equally double-click on your symbols themselves, so the dot, for instance. Other point features that might be relevant to the analysis of AMR in the environment are, for instance, the presence of hospitals. And just to point out that the data for the CTP Bardi we've added ourselves, and I've not shown you them, but there's actually we also in a quite detailed manner mapped Bardi and the variety of different industrial places, etc. The OSM stands for Open Source Mapping, and is a resource I've downloaded online, and I've just highlighted the hospitals. You can also see such things as pharmacies, etc. as well. You can change your symbols as appropriate for what you're looking for. Within each of these layers, there's the data table called the attribute table, which you can again access through right or double clicking on the name. And this was the sort of thing that would pop up. So you have your shape code, the feature class, so you can see here that within the data set there's hospitals, pharmacies, chemists, etc. And more details regarding names and districts that things are in. Moving on to the second type of vector, your line or polyline, and an example of that which is relevant to studying of AMR is your rivers and your streams. And again, this is downloaded from Open Source Mapping. They're not exact, so you do need to adjust them yourself for your own maps to make sure that they're accurate. but they're a good starting point. And for polygons, a couple of examples of polygons are, for instance, land use. So here in green is a polygon with the forest. Industrial units are in this sort of beigey yellow. Another example of a polygon is the districts or states, so the state of Himachal Pradesh, and there's also the district of Solan shown as well, with another layer. And the more observant of you might notice that actually all of my other layers only show data within the district of Himachal Pradesh, and that's because my computer's super old and didn't like running multiple layers of data from across India. So one of the things that you can do with your data is clip it to one layer to the elements within another layer. So I clipped all of my data to be within Himachal Pradesh. And then actually, if I'm honest, I regretted it slightly later, but that aside, I think it demonstrates it quite well. So for the raster data, I haven't actually plotted any myself, but I've pulled out from the literature, which is referenced here, a digital elevation model of India with the different colours representing the elevation. And you can use this on a smaller scale, and it's particularly useful for defining such things as water basins for water catchment areas. So that's the whistle-stop tour of how to add data to a map. If you're interested in doing this, I could recommend some of the tutorials that ArcMap have. There's one on Rondonia in the Amazon rainforest, which walks you through all of these steps, including going on further to do some geostatistics on the data, and then produce some images which would be suitable for publications, etc. And I think it's really worth, if you are starting out, going through a few of these tutorials to really get to grips with it. So there's quite a lot of different elements to use in the GIS. And for the last few minutes, I want to talk about some examples of analysis which have been done using geostatistical, the geographic information systems. And that's coming back to the UK, again, looking at antibiotics and the fate in the environment, and that's in the Thames catchment. And if you're interested further in this data, it's been published on bioRxiv. I've been involved in this project, but it was James Delaney at Warwick and Holly Tipper at CEH, Oxford, UK, who did the mapping and analysis. So these are maps from the Thames catchment, and the sampling sites. So first of all, looking at the map over here, so this is the UK, and the Thames catchment is shown in green, which is enlarged here. And you can see the river system, and here on the map you have your lines, which are the rivers, the polylines, and they've been coloured in differently for the different tributaries of the Thames. Just to point out, you've also got your polygon showing your drainage basin, and you've also got the sites of sampling in green dots and red dots. And the difference between the green dots and the red dots are that the type of analyses that were done on them. So it's the green dots that I'm going to be going on to look at. They had the more detailed analysis, including the metagenome analysis. And then on the right hand side of the screen, we also looked at antibiotic levels in all of these sites, and I'm just picking out a couple of them here. Trimethoprim and a sulfonamide here showed significantly different levels both between sites and between the seasons of sampling as well, with trimethoprim being particularly high in a number of sites such as Ray 4 and Ray 6, and almost always being higher in the winter as well. So the weather in the UK is quite different from that in India. So we're observing quite different patterns in India, where you have the monsoon season versus the dry season. In the UK, we always have rain. But in the winter we have more rain, and that impacts considerably on the riverine system, in particular because the wastewater treatment plants can't cope with all the capacity of rain, and effluent is released, which is untreated, which does affect what's happening in the river, and that is more likely, not only happens, but it's more likely to happen in the winter. Other things that you can analyse are the land use, and so here again you've got your tributary map in the Thames catchment area, and these are the boxes which are amplified out, if you like, and you can see that the land use, with the key here, changes. So up here, for instance, it's largely improved grassland in pink. In the Ray 2, it's very suburban and urban, with the suburban in blue and the urban in green. Whereas Lambourne 3, for instance, has a lot of arable and horticulture as well as some grassland. And Cut 3 is quite mixed, with improved grassland and suburban and urban. You can also do distance correlations. Wastewater treatment plants are of particular relevance, but also things such as fish farms, other farms where you might be having runoff into the rivers are also of relevance, and you can do geostatistics using your geomapping. Here we looked at the trimethoprim concentration at each site versus the distance from wastewater treatment plants. So these varies were log transformed. It's non-parametric, so a Spearman's rank correlation has been performed, and there's a negative correlation, as you can see here, which is significant, with distance from wastewater treatment plant. And if you look in a little bit more detail, it's not just distance from wastewater treatment plant, but it's also the type of wastewater treatment plant. So the tertiary wastewater treatment plants were closer to the sites with the highest levels of trimethoprim, whereas those which had lower levels had secondary wastewater treatment plants. Coming back to the land use correlation, and here focusing on the 4 sites with the highest trimethoprim levels, they showed, versus the sites with the lowest trimethoprim levels, they showed quite different uses in land use. And the most striking one is the increase in the urban and suburban in the blue, in the sites with high trimethoprim levels. So in the low ones there was considerably more arable. The pasture stayed reasonably constant, as did the woodland. So it shows that the urbanisation is correlating with the high trimethoprim levels, and the urbanisation is also correlating with the tertiary wastewater treatment plants, and I'm not showing this data, but also the higher population equivalents as well. So to conclude, GIS systems offer a very powerful and flexible and very visual way of exploring georeference data. And hopefully I've provided a flavour of the different steps needed to create a map in GIS software. What I haven't really looked at due to time constraints are ways to present the finished maps in a polished manner, but that's also a really important aspect of the package for producing publication quality or presentation quality images. And then used some data that's been analysed using such methods to show you the sorts of analysis that can be performed in this particular field of antibiotic fate in the environment. Though I'm always aware that it's always the tip of the iceberg, and everybody has different interests, and there are many different ways to use these packages. And I'm really looking forward to hearing the second part of this talk, which looks in more detail at spatial interpolation. So that remains just a couple of thanks. So Liz Wellington and group, particularly Chiara Borsetto and the rest of the wider Res Farm project, And then it's important to thank James Delaney and Holly Tipper and all the other contributors to the Thames project as well, and also to all of you for your attention.
Thanks a lot, Emma. I learned a lot from this short talk. Thanks very much for that.
You're very welcome.
Right. Try and share my screen.
Yes, can see that.
Okay, good. Right. Okay, so I'm going to try and give an introduction to creaking and geostatistics. So I'm not really an expert I'm not a statistician and stuff. So it's going to be, I'm just going to try and illustrate how these methods work is what I'm trying to do here. So what is creaking? Basically a method for doing spatial interpolation. And I think most of us know what that means to do spatial interpolations. Basically the process of using observations of some kind of variable at known location to estimate the value at unsampled locations. And there's a number of different methods you can use to do this. People will maybe be familiar with linear interpolation, nearest neighbor, inverse distance, weighting interpolation. And what characterizes these are that they are all deterministic methods. So they just provide like a best estimate of the value at the unmeasured locations. So creaking is different to this because it's a geostatistical method. So not only does it provide a best estimate at the unmeasured location, it also provides a measure of what is the uncertainty or the error associated with this estimate. And that's the huge advantage of using creaking for interpolation. So how does creaking work? I think the key thing to understand is that you're basically assuming that the variable you're doing interpolation of originates or is like a spatial stochastic process. And that sounds horrible, but what it basically just means is that you're assuming that at every single unmeasured location in space that your variable is a random number that fluctuates around some mean value and fluctuates in some specified way. So what you need when you do this kind of creaking is you need to define a global mean or trend function for the variable you're considering, and you also need to define a model that describes the fluctuations and the spatial autocorrelation of the variable you're considering. And the fact is, if you can do that, that actually allows you to generate random realizations of what your spatial variable might look like in space. So that's what I've tried to show in the figure here. There's just two examples of random realizations generated with the same spatial stochastic process. And we can see that they share a lot of characteristics. So they have similar amplitude or size of fluctuations, and the period are similar as well. And we can also see that if we look at 2 points close to each other in space, so x-axis here is just the x coordinate, and up here it's the value of whatever quantity we are simulating. But we can see the 2 points close to each other have very similar values. So this suggests that there's some autocorrelation for this particular variable. So how do you describe these fluctuations? That's quite critical to creaking and to these approaches here. And or I should say, often you assume that the fluctuations can be described as a normal distribution or a multivariate normal distribution. And that this is basically described through what we call a variogram model, which is what I've shown here to the left. So this is the variogram model that was used to generate these realizations. So the variogram essentially just shows what the variance of your data is as a function of distance between the data points. So in this case here, like when we have data points that are very close to each other with a short separation distance, the variance between those points the values of those points will be very low. And we see that the variance will increase as distance between points increases. And in this case, it sort of reaches a plateau. So if you have spatial correlation in your variable, this is the kind of picture you would get. And the variogram can kind of be characterized through like a few sort of parameters, which is also what I've tried to indicate on the figure here. So this is just the value that it sort of plateaus at is called the sill. And here I've just generated two different realizations, one that has a large sill and one that has a small sill. And we can see the differences in how big the fluctuations are. That's kind of what the sill determines. Then we have the range. That's the value at which data starts being uncorrelated, basically. So it doesn't really matter once you get above the value of the range. It doesn't matter if you are, in this case, at 10-meter difference or at 40-meter difference, the variance will be the same. So they're sort of equally uncorrelated. So again, if you generate two random realizations, you can see that the red one is the one with the short sill. So we have much shorter periods, if you like, in the fluctuations, whereas the black one is with the larger scale range, where the periods are a bit longer. And finally, we have what is called the Nugget effect, and that's just like what's the variability at zero separation distance. So it's kind of that represents kind of micro variability in your variable, and it also you can't really distinguish this from measurement uncertainty as well. And if you have Nugget, what that just means is that you end up like with like the variable you're looking at becomes kind of discontinuous, because 2 points, even if they are separated by the smallest of distances, there can still be a difference between the values because of this Nugget effect. So far, I've just been talking about how you can generate like random realizations from a stochastic process. When we talk about creaking, what we're interested in is obviously a realization that not only honor the stochastic process, but also matches our data points. So if you imagine that you just generate lots of random realizations, then from your stochastic process, then in the end, you only want to keep those realizations that matches your data. And if you imagine that you just do that millions of times, then take the mean value of all those realizations, which is what I've illustrated here. So the black line is now the mean of all the realizations that match the data and honor the stochastic process. Then that is exactly what it means to do creaking interpolation. And if you take the variance of all those, then that's exactly the error variance that creaking provides. And obviously, when you do creaking, you don't have to do all these simulations, take the mean of them. There's equation that allows you to solve the interpolation problem. So for just the mean and the variance at every single point in space. Okay, so here I just tried to show what is the difference in the creaked values if we use 3 different variograms in this case. So actually what we see is the sill, the black and the blue has the same range parameter for different sill, but we can see the interpolated value is exactly the same. So the sill doesn't actually have an impact on what the interpolated creaking value is, but it has an impact on what the uncertainty is So we can see these are the plus minus the standard deviations around the estimated value for the blue variogram, and the black one is the one here. And the green shows the result if we have a short range. And well, yeah, it's a bit of a funny result, this, but basically what this shows is because the data points in this case are separated by 10 meters, but the separation distance or the range for the green curve is only 5 meters. It means that it automatically will draw the creaking estimates towards the mean of your the process that that you've defined. Not sure that was particularly well explained. Anyway, that's just like kind of to give an understanding of what it means to do creaking. I should also say that also the creaking estimate is generally much smoother looking than the underlying process. That's also an important point, I think. So the key is then when you do creaking in practice is obviously how do you actually identify these geostatistical models that the creaking is based on, and this is what you do through an explanatory data analysis. So there's a number of things you could consider here. As I said, creaking becomes sort of, from a practical point of view, it's at an advantage if the data that you are trying to interpolate can be assumed to follow a normal distribution. So you can, like one way you can look at that is just basically do a histogram plot or a box plot, like what I've done here, of some concentration data. And we can see in this case, which is often the case with concentrations, that it's quite a highly skewed distribution. So when people do creaking and these type of analysis, it's quite common that you introduce a transformation. In this case, the concentration has been log transformed, and we can see the resulting log transformed distribution of the data is much more symmetric and normal distributed looking. So this is a much nicer variable to be working with in space for the creaking. Another thing we need to be aware of is whether there are any obvious trends in the data. So in the examples before, I was just showing how it looked if you're assuming that the global trend that your data varies around is constant. Here we have an example again of some concentration data that looks highly skewed here. And here the concentrations are plotted. This is from a transect across a plume in groundwater. And the data have been plotted. It's a quantile plot. So the red ones are the highest 25% of the values, and blue ones are the lowest 25% of the values. And we can see there's an obvious trend here. So assuming a constant mean for the creaking in this case is probably not a very good choice. So in this case, we could use an analytical trend model to represent the trend. And if you subtract that trend model from the data, we can see that the residuals you get are then much more sort of follows a nicer normal distribution. And this is then what you would do the creaking estimate on. And finally, like probably the most important part of this explanatory data analysis is to try and determine this variogram. And the way you do that is you calculate an experimental variogram, and basically you just look at you calculate. I don't know how to explain this. You calculate you take all data points that are, for example, in this case here, located within 0 and 100 meters of each other, and then you calculate the variance of all those values. Then you do the same for the interval from 100 to 200 meters in this case, and calculate the variance, and from 200 to 300 and so on. And in this case, this is a nice example. We can see that the experimental variogram really displays this autocorrelation structure very nicely. And you then have to fit a theoretical variogram model, and there's a number of different models that you can use to try and capture this behavior from your data, because that's then the model you need to use in your creaking estimation. Yeah, so once you've identified a model, you can then do the creaking, and it's then good practice to try and validate your result using different techniques. I'm not going to go into huge details there, but the validation could, for example, be try and sort of remove some of the data from your data set and see how well you can predict those data points with your creaking models. So this is just a summary of the creaking. So basically, the method provides a best estimate and the variance of the variable of concern. It also allows you to do these kind of conditional simulations, as I showed before, assuming that you know or can assume a good probability distribution, which is typically assumed to be a normal distribution. As I also showed, that when you do creaking, the data you're having are actually used in two phases. So you use it firstly to do a structural analysis to identify the variogram and the structural part of the geostatistical model, and then you use it subsequently for conditioning or for the interpolation itself. And the way you identify your geostatistical model is through detailed explanatory data analysis, and here you have to be aware of like when you do this analysis, whether your data are non-normal, whether they have non-negativity as well, like something like concentration data can't be negative. So if you start doing creaking on concentrations and you're not careful with how you define your model, you can end up getting negative concentrations, for example, or get uncertainty bounds that include negative concentration. So you have to be careful with these kind of things. Then, as I showed, the trends are important to consider. You can consider an anisotropy in your parameter or in your variable as well. And then there's a whole aspect of whether you need to remove trend or if you need to do a transformation of your variable. And if you do that, then you just have to be aware of this when you do your back transformation to the original variable. Yeah, and then finally, validation is important. And then I haven't really had time to go into like advanced applications of creaking. You can do co-creaking as well of multiple variables. So this is quite handy if you, for example, looking at how like something like, for example, groundwater levels is quite an expensive thing to measure because you need to drill bore wells and stuff like that. But you can maybe predict that quite well from topography. So that's an application of using limited groundwater level data together with topography to create a groundwater level map, for example. There's also examples of using these kind of creaking approaches for sampling design and for more sort of clever sampling design, and because you can sort of assign value of getting new information using these kind of creaking approaches. So I don't know, maybe I didn't really hit the brief with this, but that was just to try and give you a quick overview of what it means to do creaking. So that's it.
Thank you a lot, Mats. You did hit the brief, and again, I learned a lot from your talk. Thanks a lot. Both Emma and Mats said they are not experts on the material, but I think they've shown that actually they can teach us a lot. So thanks very much for that. We have a bit of time for questions on either presentation. Are there any? You can ask questions in the chat, or just unmute yourself and ask a question straight away.
So
Yes.
thank you both, Emma and Mads. Absolutely brilliant introductory material and really lovely samples, examples rather, because it's so much easier to follow when you exemplify it. And I think Mads, particularly, I'm interested in because I've done kriging in a lot of the work over the years, and I've sort of always wanted a sort of better feedback about sampling. So you mentioned at the end that it's really important for sampling design, and this is something I always struggling with because you have all these biases. It's so hard not to be biased. So I believe in our sampling in the Indian project, maybe less so in the Thames, but certainly in Buddy, we have been kind of influenced by things. And so how can you test if you can see that you've missed a predicted area of interest from the extrapolation of the variable data? Can you then input that data, and is there some measure that you can show that you've reduced the bias? What way of proving that have you?
It's a really good question, Liz, and I have to say this is not really an area I have actually sort of been using these geostatistical methods and before. It's something I've seen, so I don't think I have a really good answer for that. One thing, when you look at for example, this is just a map of some concentrations that have been mapped by kriging.
Yeah.
So we have the mean values here, and then we have the variance or the uncertainty. What we can see is at all these dark spots, that's where we have a measurement point.
Yeah.
Around those points, we have a lower variance because of the autocorrelations in the variable. So you could say that where you have most uncertainty and where you could perhaps gain most is by sampling in the areas where the variance is high. Is a simple way, but there are like more sort of clever ways of doing this, and you could even, I've seen it in sort of in groundwater investigations, because measurements are so expensive, so you can include almost like an objective function that takes into account the cost and the likely output you might get if you drill a new borehole. Is that actually worth the reduction in uncertainty and things like this? But yeah, so I'm not really sure I have a really good answer for
that. No, but that's super helpful, and I think I'll have to spend a bit more time with the engineers. So they're not very good at sort of transferring their expertise, and you did a superb job of explaining it. So thanks very much.
So maybe one thing I would add is that when you do kriging, and that was kind of what I was trying to say with the slide here, is that the kriging estimate is always smoother than the underlying process. And what you're actually assuming is that the true variable is one of these random realizations. And obviously we'll never know which one is the correct one. So it's the kriging is just the best estimate of that. And what you often see, and I know again from groundwater application, which is a bit dangerous, is that people actually use the kriging estimate, for example, of like the permeability of the groundwater media. Then they do a kriging estimate of that, and then they use that to drive another model that relies on the hydraulic or the permeability, for example, to calculate groundwater flows or how the ground, like contaminant plume is in groundwater. And that's really quite dangerous because there might be like a complicated, a non-linear relationship between how the creaked input is related to what it is you're actually interested in. It could also be rainfall data that you might want to drive a hydrological model. Rather than using the creaked input, it's sometimes better to use the conditional simulations to drive the model. Yeah, I don't know if that made that just confusing.
No, I follow. Yeah, that's. I think that's what I was kind of not wanting to do, but realizing it was probably going to be necessary. So I think it's absolutely essential to have models as well. And that's the key thing you always learn, is that the modeling starts at the beginning of the project, not at the end.
Yeah.
Which I do think is important for India, that because we were all a bit strapped for cash, that modeling something that it's a little bit easier to cut if you're a wet scientist. But it's the most important thing, because it really has an impact on how you do the sampling, and that's that's your essential stuff that you do at the beginning, and I think really drives the problems of bias if you're not careful. Yeah, brilliant. Thanks very much.
Yeah, thanks all again. I think we need a few minutes comfort break. Laura, are you okay with starting 2 minutes late or so? So giving a 5-minute comfort break for everyone.
Yeah, that's absolutely fine.
Yeah, if there are more questions for Mats and Emma, please put them in the chat, and we might come back to that or answer questions in the chat if you have any more questions. So see you in 5 minutes. Okay. Laura, I think we should be starting soon. Maybe already start sharing your screen. Okay, good. See that.
Can everyone see my slides and hear me?
Yes. Shall we start? Laura, what do you think?
Yeah, I'm happy to.
Okay, good. Great. Then let's do that.
Great. Okay, so thank you, Jan. And I just want to say thank you now as well for organising this whole workshop series. I think it's been great to hear about aspects of other people's projects, but also learn some new skills. So while I've got the opportunity, just to thank you for organising everything. Okay, so to begin, I guess, my talk, what I'm going to focus on today is the analysis of contaminants of concern. So I've prepared this presentation, and when I was creating it, I feel that I've maybe touched on so many things I haven't gotten into enough detail about particular aspects. So I'm happy to follow up on anything if anybody has any other questions, or if you'd like me to come and do another talk on something in particular. But just today, what I thought I'd introduce is starting with sample collection. So I think it's interesting that Liz asked the question around where to sample, because I think this is a battle that I constantly have. So I'm going to touch on thinking about sample frequency, types of sample collection, storage, and some shipping, and then move on to think about sample treatment, so cleaning up the samples and concentrating them, including the use of standards, so internal surrogates, and then moving on to the analysis section. So I'm going to briefly talk about direct injection as a method of analysis, and also using SPE, LCM, SMS. And what I'm going to focus on is targeted analysis, but then at the end, I'm also going to talk about some recent mass spec advances where we can think about doing some more sophisticated non-targeted analysis. And then lastly, I'm going to hopefully point you in the direction of some useful resources and some methods and some protocols. So I just want to say that the presentation that I've pulled together, so this has been built on a mixture of published literature. So there's a lot of really good research on this at the moment, as well as based on my experience working on sampling and monitoring campaigns. So hopefully I've got a good balance here, but I'll say that all sources and all references should be on the slides, but I'm happy to share any papers or reports if they would be of use to anybody. So I guess the reason why I want to include sample collection, because I think it's important when you're thinking around sample analysis about where the samples actually came from, to ensure that they're representative of what you're trying to measure. So I think Liz alluded to this really well. So ideally with a monitoring campaign, you want it to be devised so that it gathers this spatiotemporal picture of chemical pollution. So you would take samples regularly and at a catchment scale. And I've drawn a quick sketch here as an example of a relatively small sampling campaign. So you can see the point of discharge at the wastewater treatment plant. And then this is where you would sample to look at the immediate effect. And then you could ideally sample further downstream so you can evaluate the chemical fate. And what you really want to do is to be able to compare your sample to a pristine site, so typically upstream. And this is where you would have a sample that's free from contamination, and it was used as a background. However, I'm sure that, as most of you are aware, when you're carrying out monitoring campaigns, it's actually quite a challenge to find a site that's free from any form of contamination. Even in the UK, we've trekked into the Yorkshire Dales to try and find a background site, and we still managed to find some contamination. So an upstream site, it's a bit of a caveat just to say it doesn't always mean that it's a clean and background sample. And when you're thinking about your method reproducibility and quality assurance, quality control, what's really important to do is to collect blank field samples. So this is typically, you take some HPLC water into the field and you would treat it in the same manner as you would with your actual environmental sample. And this is just to check for any contamination in the field through sampling all the way through to sample prep and analysis. So now in terms of the actual collection of the sample, for pharmaceuticals analysis, this is quite often done with a grab sample. So you can get grab samples of water from milliliters to liters, and it's suitable for moderate to high chemical concentrations. But what you often find is that it fails to detect trace levels and only really shows this single snapshot of chemical levels at a specific point in time. So an alternative is to do passive sampling, and this collects water directly in situ. And so then you get the accumulation of pollutants over time. And this is what I'm going to go into in more detail in the next couple of slides. But I guess ultimately what you're looking for is to collect samples with sufficient spatial resolution that you can build these concentration profiles and increase your probability of detecting these transient and tricky pharmaceuticals. And I think when you're devising your sampling campaign, this is important to do, but obviously you are then met with the logistical challenges of where you're actually sampling. So where to collect your sample? I think one of the main drivers of this is largely the size of the water body that you're dealing with. So in large rivers, there's more chance of variability in water characteristics and quality of the water across the river. There may be a tributary coming in, for example, from above the sampling point, or you may get a wastewater treatment outflow pipe upstream, and it takes longer for the water in a river to typically mix. So this means this takes longer for your chemical to mix and become this ubiquitous presence in the water. So if you were to take one sample, for example, on the side of a river near a discharge point, then this might not be representative of the whole river stretch that you're interested in. So it's important to bear in mind that this isn't an accurate representation of the pollution load. So the figure on the right-hand side of this, this slide is taken from the supporting information of the paper by Emily Burns, who I worked with on a monitoring campaign in York. And she designed this study to look at chemical variability across a river stretch by taking a lot of repeated samples at 3 points across the river, and then comparing chemical concentrations with target analytes. And it's probably important to point out here that our rivers in York are relatively small. So we found that these were well mixed. And as you can probably see by the charts in this slide, there was little variability in the chemical composition across the river. So what we were able to determine here was that a single sample, whether it be in the middle or at the edge, was sufficient in order to give you this accurate representation of chemical concentrations. So this is, I guess, an ideal if you can do some preliminary work to look at the concentrations and devise your sampling campaign as to where best to sample. But if this isn't possible, what you can do is take water quality parameters to understand if your water is well mixed. And if it is, then this would suggest that there's only a need to take limited samples to get this whole complete picture. And it's just a note really, is that when you're planning your sampling sites, it can be really useful to plan these around access to bridges. So this is something that we've done in the past, as well as looking into the use of boats, for example, if you need to get this stretch across the river rather than just a single sampling point. So I guess when I started doing chemical monitoring, I had this grand idea that I would be using some fancy high-tech equipment, and I could potentially be floating across a river and collecting some wonderful river samples. But in reality, what it ended up being was me finding lots of bridges and pulling up large quantities of water, which is quite hard work, especially in the British rain, as it was mentioned, and lugging up buckets up 30-meter bridges. So this is a grab sampling collection. And when you have limited infrastructure or capacity for this advanced sampling techniques, then grab samples are really useful and they're a cheap option. And as the name suggests, it's literally a case of grabbing some water. So you can do this in a bottle, you could put a bucket in a river. It's literally taking a portion of water for analysis. But most pharmaceuticals and metabolites transformation products exist in our environments at trace levels. And on the whole, most water samples tend to be collected by grab samples, but this, as I mentioned before, only means that you're measuring this instantaneous concentration at a certain moment of time and doesn't necessarily reflect this average concentration of target substances in the water. And this slide, I think, is really important to highlight how you have to be careful about when you select your time to do your sampling. So the grab samples don't capture this diurnal variation in chemical concentrations. So I've put here a figure taken from a study by Monroe and colleagues published in 2019. And this was a 12-hour diurnal occurrence study. And it was conducted in London between the time of 7 in the morning and 7 in the evening. And they collected water samples during this period every hour. And this sampling site was in the Thames, so central London. And what we know about the Thames is that the water levels change on a daily basis and can be up to about 7 meters. And this typically occurs twice a day. And the river flow is actually relatively small compared with the volume and the tide. So on the plus side, it is relatively well mixed. So coming back to this figure, so the black data points represent the mean of 2 grab samples that were collected, and the grey dashed line is the tide height at the time of sampling. And what you can hopefully see here is that the time of day the samples were taken strongly influences the measured concentration. And probably what's most relevant to our program is that the levels of antibiotics in particular are seen to vary most throughout the day. So trimethoprim and sulfamethazine were the only, the most obvious cases that showed any correlation with tide or water conductivity. And in fact, these almost doubled in concentration with high tides. So I think if you can look at chloramphenicol, the concentrations range between 5 and 25 nanograms per litre over the course of the day. So in terms of data interpretation, it's really important to think about how representative your sample is. So if you take this example, if you were to sample in the morning, this would underestimate your average concentrations. So the next sampling technique I'm going to talk about is passive sampling. Passive sampling has recently become a major tool when you're looking at organic contaminants in surface waters, groundwaters and wastewater as well, in fact. And a whole suite of contaminants have been studied using passive samplers. In addition to prescription drugs, you can also see illicit drugs, pesticides, PAHs using this sampling technique. And the passive sampling really overcomes some of the disadvantages that I've talked about when you're talking about grab samples. Because in theory, it objectively reflects the overall pollution situation of your substances in the surface water. So a polar organic chemical integrative sampler, or POCUS, has been really well used for studying the presence of pharmaceuticals in the environment. And this is a relatively low cost device. It's non-mechanical and it's quite simple in design. So this slide just shows the concept of POCUS in a bit more detail. So it comprises of this receiving sorbent, and it's enclosed between two diffusion membranes. And to prevent the loss of these membranes, you encase this within some O-rings, and these are typically made of stainless steel. And you sandwich your sorbent in between all of these rings, and it's placed most often in like a metal basket, which is then left in situ in the field. So the idea is that large substances, so thinking about bacteria, macromolecules, particulates, are excluded from this device, but it can capture your trace contaminants. And there are a number of different configurations for this sorbent material in the middle. Probably the most relevant is the pharmaceutical POCUS, and this is a hydrophilic lipophilic sorbent, and it's called the Oasis HLB, which is made by Waters. And this is a water wettable reversed phase sorbent. And so basically it comprises of this, this polymer that can absorb all of the chemicals. And yeah, so Oasis HLB is probably the most frequently used in this case. And it's been widely used for pharmaceutical detection, including antibiotics. So at the moment, this all sounds great. But if you're going to use these quantitatively, then they require quite some effort to calibrate them. So you need compound-specific uptake and diffusion coefficients, which require quite a lot of work to generate, and they can be determined both in situ as well as in the labs. And you also have to deal with potential losses of the resin or sorbent. So even though they're encased within this system, sometimes you can lose the resin, and then you need to account for that when you're doing your quantitative calculations. And lastly, the final option I'm just going to briefly introduce is a composite sampler. So like passive sampling, it's effectively collecting the pollutants over time. So you get this more comprehensive picture of contamination. And what you do is set the collection samples at the frequency and the volume you use. So here I just provided the example that we've used before. So it was 24 hours of collection, and every 30 minutes where 50 ml was collected into this big tank. However, the downsides are these are relatively expensive, and I've seen a lot of studies place them in wastewater treatment plants, for example. But if you were to typically leave these out in the field, in a river, then I wouldn't guarantee that it would be there by the time you get back. So potentially some downsides here. And again, if you were going to use it for quantitation, then you need to do some in-field, in situ measurements to get the data and combine this with information like flow so that you can determine concentrations over time. So now moving on to sample cleanup. So you've collected your sample, and what you need to now work out is what to do with it. So the two options that I'm going to focus on are SPE LCMS-MS, as well as direct injection LCMS-MS. So direct injection prep is very simple. In the field, you would filter your sample after you've collected it. So typically you use a glass fiber filter and you put it into the LC vial for analysis. And the filtration step removes the particulates and the bits that you don't need, but retains the chemical within the solution. And what there's been a number of studies that have shown that there's quite minimal retention on the actual filter, because I think this was a concern in the beginning. So one study that I'm familiar with looked at about 26 compounds with different properties. So it's acids, bases, amphitars, had chemicals ranging in hydrophobicity, and they found that the losses were less than 5%. So as I said, relatively simple. You take your sample, you filter it, and then it's ready for analysis. And I'm going to talk about the analysis step later. You typically have to inject a larger volume into your mass spec for your analysis, but effectively your sample is ready to go. Whereas for SPE, so this is solid phase extraction, you have to take your samples back to the lab where the SPE process, it cleans and concentrates your sample. So it's a more involved process, but it can take various forms. It can be done online in the mass spectrometer, as well as offline using cartridges. And when I looked into this a bit more for this presentation, I found quite an interesting review on monitoring studies to evaluate the different techniques they use for sample prep. So this was between the period of 2018 and 2020. And what they found were that quite overwhelmingly, classic SPE procedures were most commonly selected when you're thinking about sample prep. So this was mostly cartridges that were used offline. So in about 70% of studies, whereas 16% of studies use different methods, which would include, for example, direct injection. So coming back to direct injection, it's relatively simple in terms of sample prep, and even though it's not as widely used as SPE as a method, I think it's gaining prominence in terms of a reliable method to determine pharmaceuticals in river samples. But on the counter argument, SPE has many benefits. If you have particularly mucky samples and filtration just won't work alone, then SPE will be necessary. As well as if you really need to concentrate your samples, then SPE is something that you can do for that. So just now what I'm going to do is go into a little bit more detail about solid phase extraction itself. So SPE is a form of liquid chromatography. And it's widely used for organic analysis of agrochemicals, pharmaceuticals, and other contaminants. But the basic principle of SPE is that your compounds of interest, they partition between two phases of solid and liquid. So there must be a greater affinity of your compound for the solid phase than for the sample matrix. So your water sample that's collected from the river. So what you want is your sample to come through the cartridge and the chemicals to be retained on the solid phase. And then you would then elute these chemicals of interest with a solvent. So the solvent that retains your pharmaceutical, your chemical, is encased within this barrel syringe. And after you activate your sorbent, you pass your water through. So this can range up to hundreds of mils. We've passed liters, up to about 1.5 liters of water through a cartridge before. And then, as I said, your contaminants are retained on the sorbent, and the water is then discarded, comes out the bottom of the cartridge. And then you elute your compounds of interest using a few mils of solvent. So this is a relatively time-consuming process, but if you're dealing with trace level analysis, this is really important. And SPE, there are many different cartridges that you could use, but they typically separate your compounds based on the principles of reversed chromatography. And there are a number of different characteristics which I've sort of included here as to the types of target chemicals and the best types of sorbents and SPE columns that might be useful in the future. But typically for pharmaceutical analysis, what tends to be used is an Oasis HLB cartridge. And I just want to introduce this paper here by the Diana Aga group. And I think it would be potentially of interest to quite a number of people working in the program if you haven't seen it before. So it's describing methods for the measurements of antimicrobials in wastewater and surface waters. And they have done a really nice job of validating the various steps in sample prep and sample shipment. So here they talk about SPE methods that might be of use to you, but I'm not going to go into the actual SPE method itself. But what I think is the thing I'm going to talk about is actually thinking about SPE as a method of sample shipping. So performing solid phase extraction after you've collected your sample is great because firstly, your shipping and your handling costs can be minimized because you're only shipping the cartridges rather than glassware filled with all these liquid samples. And secondly, there's less chance of your samples breaking if they're retained on these cartridges. And as I mentioned in this paper, they talked about validation steps and investigated the stability of antimicrobials in SPE cartridges. And they tested them under two different storage conditions that would typically be found if you were shipping these samples. So they had -4 degrees and room temperature, which was defined as around 23 to 27 degrees. So these were defined as worst case and best case scenarios. So the best case would be to ship on dry ice, and the worst case would be to ship at room temperature. And the antimicrobials that they evaluated included sulfonamides, macrolides, quinolones, and tetracyclines. And in general, what you can see is a decrease in analyte recovery over time for the compound classes. So I think this is to be expected, really. The stability of the analytes inside the actual cartridge also differs by compound class. So your sulfonamides and your tetracyclines show much faster degradation than the macrolides and quinolones, which tend to be more stable inside the cartridge. However, I think the most important point to note is that cold storage increases the stability of the compounds significantly. And it shows higher recoveries of the analytes from the SPE cartridges, even after 1 week of storage. So by keeping the cartridges cold during the shipment, the integrity of the sample is ultimately maintained. So if you ship your samples at room temperature, you typically be underestimating your concentrations because you would have this degradation occurring that you're not accounting for. So you have your sample in an LC vial, and this has either been filtered in the field ready for direct injection, or it's been concentrated and cleaned up by solid phase extraction. And so the next part is the analysis. And when I first started working with pharmaceuticals in the environment, mass specs were incredibly hard to get your hands on, and we used to do a lot of work with HPLC UV. It's really cheap, robust, relatively straightforward. However, when you're dealing with complex environmental matrices with multiple chemicals, then its specificity is one of the drawbacks that you have to consider. So this reason, mass spectrometry became a really big player when you're looking at the presence of pharmaceuticals in the environment. So I guess to try and explain LC-MS, it's probably easiest to split this into two parts. So the LC and the mass spectrometer. So the LC stands for liquid chromatography, and it's a separation method. So your sample gets injected into the LC, which uses really high pressure, and it separates the sample components and then introduces these into the mass spectrometer. And this, so mass spectrometer, or MS, is the part of the analysis, and this creates and detects ions and allows you to work out what is actually in your sample. And what's important to note here is you can have both LC-MS and LC-MS-MS. So a single MS means that you only analyze your precursor ion that's generated in the source, whereas MS-MS is the combination of two mass analyzers in one instrument. So the first MS filters the precursor ion, and then you get this fragmentation of the precursor ion with lots of high energy and gas. And then a second mass analyzer then filters your product ions. And really the advantages of MS-MS are that they increase the sensitivity of your analysis. And you can get more structural information about the fragmentation pattern. So tandem mass spectrometry, or MS-MS, typically uses something called a triple quadrupole mass spectrometer. And this is what you would quite often see when you're reading papers to do with the quantification of pharmaceuticals in the environment. So the next couple of slides, I'm going to go into more detail about this. So to start with, your sample is injected into the HPLC with flowing mobile phase. And if you were to use direct injection, then typically you would be injecting around 100 microliters of the sample. But if you're using more traditional methods, then it's typically around 10 microliters. And polar compounds, such as pharmaceuticals, can then be well separated on a reverse phase HPLC column. And this is operated under a gradient option normally, where you get aqueous to organic gradient solvent flow. And then your pharmaceuticals, once they've been separated, are then transferred to the ion source. So this is just a quick figure to demonstrate a little bit more about reverse phase chromatography. So this is the column that your sample goes through. And you have your mixture of components and then a stationary phase, which is your column. And the most hydrophobic parts of your sample interact with the column best, and they get strongly absorbed, whereas the least hydrophilic components elute first. So this is how your sample gets separated and how you get the range in times of which your samples are detected. So coming back to this figure, your sample is now in the mass spectrometer in the triple quadrupole, and this is what I'm going to talk about now. So a triple quadrupole mass spectrometer. So this is the MSMS. And here you've got 3 quadrupoles. Your first and your third quadrupole, these act as mass filters. And the second causes this additional fragmentation. And a common sequence here is you get a product ion scan, then you get a precursor ion scan, and then you get a neutral loss scan. And then it's followed by selected reaction monitoring or multiple reaction monitoring. So this is just to demonstrate the output that you would typically get from a mass spectrometer. This is a target ion trace of a spiked pharmaceutical standard. And what you now need to do is to process and interpret your samples. So a major challenge in analytical chemistry is the development of repeated sample preparation methods that give you these acceptable and reliable recoveries that can guarantee the correct representation of your result. So you have to consider the potential for matrix effects. And this is something that's quite widely reported for the analysis of environmental and biological samples. And a lot of this has been linked to the presence of natural organic matter. But from what I'm familiar with, this mechanism still hasn't really been unraveled. But what you're doing is really developing your mass spec methods to minimize the matrix effects. So you can use different methods of extraction, of cleanup, of elution. So filtering is one aspect of this. Solid phase extraction, as we talked about. You can do different liquid chromatography procedures, as well as reducing your elutant flows, for example. However, the problem is when you try and apply these to simultaneous analysis of a whole suite of compounds, you get varying degrees of ion suppression and enhancement. And so there's been a number of methods that have been proposed to compensate for this, using different calibration techniques. So this is where concepts such as standard addition, surrogate monitoring, and various forms of internal calibration come into the analysis. So isotope dilution is a means to compensate for matrix effects, and it's generally considered to be one of the most recommended and most versatile approaches when you're dealing with matrix effects. So when thinking about internal standards, you have to consider a number of things. So your internal standard shouldn't be present in any of the samples analyzed. For example, so if you're using a prescribed drug as an internal standard for a therapeutic drug monitoring campaign, it's not a good idea. It also needs to be similar in the physicochemical properties to your target analyte. So good ideas here are isomers or homologs. And an important point, I guess this brings me to, is the discussion around terminology of internal standard, surrogates, external standard. And I think that the nomenclature around internal standards is not entirely clear. So different people call these different compounds different things, typically based on when they're added to the analytical process. So analytical internal standards can be added as late as just before the injection into the HPLC, and sometimes they can then be called injection standards. And this is basically used to provide a reference of instrument detection variability. However, if your standards are going to be used for correcting your extraction and cleanup recoveries, then they needed to be added as early on in the process. And so sometimes people use multiple internal standards added at various different points to account for all possible sources of variability. So just to recap, if you add your internal standard at the beginning, this is typically called a surrogate. And this is when you can account for errors in sample preparation. If it's added just before the injection and analysis, then this is more likely going to allow you to account for recoveries and instrument variability with the instrument specifically. So typically when you select an internal standard, the rule is that whatever happens to the analyte or your compound of interest will happen to the internal standard. And most often we use an isotopically modified version of the target analyte. And what we want is that we don't want these isotopically labeled internal standards to separate from our analyte when we're doing the liquid chromatography, but we want them to be separated by their mass difference. However, isotopically labeled standards are expensive, and not all analytes of interest have a corresponding labeled standard. So in this case, a number of reports have suggested using a corresponding internal isotopically labeled internal standard, such as atrazine. But there are the options are typically deuterated, carbon-13 or nitrogen-15 labeled compounds. And I just wanted to point out here, when I spoke to Jan recently, he was asking about which isotopically labeled internal standards to use. And I've always used deuterated internal standards. And I think a lot of methods that have been published in the literature use deuterated internal standards. But when Jan asked why, I started to look into the literature a bit more. And in the chromatography literature, it's suggesting that, but in the mass spec literature, sorry, it's actually suggesting that carbon and nitrogen labeled compounds are generally more preferred because you get less of a shift in the retention time in comparison to your analyte of interest. Whereas the deuterated compounds, you get a bigger change. But I think the published methods for pharmaceutical analysis in environmental samples, so the USGS method, the US EPA method, as well as other published literature sources, they all use deuterated standards. And I think what your choice really comes down to is the availability. So when I looked on some internal standard websites just now, I couldn't even see any carbon labeled compounds for my chemicals of interest. So I think availability is a large factor here, but also what can reflect your analyte most in terms of your analysis. So I'm aware of the time, and I shall probably start to speed up to give time for a question or to move on to the next talk. But really the last part of the presentation that I have put together is about quantification. So what you want to do is to use all this analysis to determine the concentrations of your chemicals of interest in your samples, or quantification. And the two methods I'm going to talk about are external calibration and internal calibration. And in external standard calibration, you plot your absolute analyte response against a known analyte concentration. And this creates your calibration curve. So in the example on this slide, I've got a range of calibration standards and then the corresponding peak areas. If you plot these, then you can use the regression to calculate your unknowns when you have a measured peak area. In comparison, when you've got internal standard calibration, so this is when you use your stable isotopes and your sample is fortified with these. So this is along the same lines, but it changes slightly and plots the ratio of the analyte response to the internal standard response. So this is called a response factor against the ratio of the analyte amount to the internal standard amount. So your resulting calibration curve is applied to the ratio of the response of the analyte to the response of the internal standard. And most modern software packages contain algorithms that automate this, but it's important that you check your peaks and these are inspected to make sure that these are integrated properly. And then lastly, what we have to deal with are issues of carryover and contamination. So it's important to have properly validated methods. And I don't have time to go into all of these, but the paper by Luz et al. In 2016 is really nice, talking about quantitative mass spectrometry and the ideas around accuracy, recovery, and precision. And another useful source when thinking about quality assurance and quality control is the paper by Ed Furlong, looking at using mass spectrometry for the determination of human pharmaceuticals in filtered water. And here they go into quite a lot of detail about the different types of QA and QC samples and when these need to be used. So, for example, the presence of a lab reagent blank, so you can check whether there's any contaminants in your sample or carryover, as well as thinking about your field blank samples, for example, that these were the ones that were prepped in the field. So I don't have enough time to go into non-targeted and suspect screening, but suffice to say that this is what I've talked about in the analysis section is targeted analysis. So when you're developing a method based on the determination of analytes that you know and you want to quantify, and these are the ones that you can then analyze and work out the concentrations for. However, more advanced mass spectrometry methods now are available, such as suspect screening and non-targeted screening, which take a more comprehensive evaluation of your sample. So thinking about unknowns and trying to identify those. Okay, so that brings me to the end. So I hope that's been helpful. And I've put a slide up with some additional resources, which I'm happy to share about water sampling techniques and methods that have been published and are well accepted in the field. So thank you very much.
Thanks a lot, Laura. Again, I've learned a lot. So thanks very much for that. We have time for some questions on that.
Thanks, Laura. Do you mind if I ask a question?
Absolutely.
Certainly, from experience of modeling antibiotics, how they behave in the environment, I know they're really annoying in the sense that they tend to ionize readily and they have multiple dissociation points. So depending on the environment or how it changes, they change their speciation. And I mean, I'm interested in the POCUS samples, because I think that gives a really good sort of integrated measurement of the antibiotic in the environment. But I wondered how the absorbent in the middle, how that copes with the fact that in a given sample you could have a mixture of cations and zwitterions, and that can change if the conditions change. So I'm basically interested in how well do those absorbents cope with that, and therefore how well do they give a representation?
Yeah, that's a really great question. And yes, ionization of chemicals is just an absolute nightmare. But I think, so for POCUS specifically, this has been validated for the use of ionizables, especially antimicrobials. The key aspect is that you have to validate your methods in situ and make sure they are relevant to your field scenario. So your uptake rates and diffusion rates, they have to be accounting for the pH of the exposure medium, and therefore the behavior of the chemical is representative of what is happening in your environment. So, and the same, I guess, applies for the analysis. These chemicals behave very differently in different water samples, depending on pH, as you advised. So a method on one instrument for a sample collected in the UK might not necessarily work for a sample collected in India, analysed on another instrument. So the methods are there and they have been used for these compounds. It's just a case of, I think, specific in situ validation for your actual experiment or your question.
That's really helpful. It's good. It's sort of reassuring to know that the problem isn't just one that's when you're trying to model how they behave. It's also a problem with the chemical analysis, and yeah, it made me think also about some of the chemistry we do as well, and how it's being performed. I just also often worry that the usual Oasis stuff is bunged in the middle and it's chucked in the river. You know what I mean?
Yeah.
And whether much thought is given to the environment in that respect.
Yeah, no, I think they have, because there are some other I know Waters have developed like a series of application notes around the use of HLB for the detection of pharmaceuticals, and include like notes around ionization. So I think they have identified the environment as quite a niche area for analysis, and they seem to be responding to that by developing the technology to account for all these complexities.
Yeah, thanks, Laura. That's really good. I enjoyed the talk.
Thank you.
I know, I just wanted to say a tour de force and pointing out where we all go badly wrong often. So really, really lovely effort and great explanation of lots of detail. Just one question about the sort of general environment is we compare sediment with the water body, and I'm just wondering how much you look at sediments in rivers, and of course it's a completely different set of problems of extraction and so on, and what your sort of thinking is about sediment and the approach to it.
I actually had some slides around sediment and soil extraction, but I took them out because I was like, I'm definitely going to go over time. So I probably should have kept them in. So I've mostly worked with soils rather than sediments, but in terms of extraction and the behavior, the principles are roundabout similar. So I think it's really important in terms of the bioavailability of the compounds. And I think that's something that we quite often forget about when we consider the environment. It seems to be focus is largely on the aqueous phase. So I think sediments and sediments in particular are important when we're thinking about risk, because they can be both a sink but also a source. So we know that they can absorb, but then they can be released. So when you, I don't know, for example, if you get a change in pH of the water flow, that might release some of the antibiotics back into the bioavailable fraction. So I think really important. In terms of analysis, I mostly need SPE because it's just a bit more tricky, a bit more dirty, more organic material. But I'm happy to share some methods. You can definitely get them out of the sediment and out of soils.
Yeah, I think we will be sharing methods. So that's one of the things that the aim, isn't it, of this whole series of workshops. So I think it's a tremendous opportunity to compare and come up with some kind of standardization, because this is the thing you really notice in the literature. And you pointed it out very nicely today, is there's so many variables and it's really difficult to compare different studies. So thanks again.
Thank you. I guess that's where modeling comes in, right? That's
indeed, but you know, it always starts with data as well. So we need good data too. But yeah, we can augment and improve our sampling, both planning stage and subsequent. Yeah, great.
Thank you.
Cheers.
Thanks a lot. If we have maybe a minute more time, there is a question in the chat from Shubham. Which technique would be better for sample cleanup of antibiotics if we have less sample, SPE or direct injection?
I think direct injection. There's so many factors that you would need to consider, like concentration. If your chemicals are in high enough concentration that you would be able to detect them, then you'd have potential losses using SPE that you maybe can't account for. So if you've got such a small concentration, a small amount in the beginning, then I think direct injection.
What volume would you think where solid phase extraction is not really suitable? Where would you draw the line?
I think most cartridges have got like specific like guidelines, but I have never put on less than like 100 mil.
Okay. Yeah. Thank you, Laura. I think we probably should do 5 minutes comfort break. So starting at 11:03 or so. So see you again in 5 minutes. Thank you. Thank you, Laura. Okay, I think we should be starting again in a minute. Start to share my screen. Can everyone see that?
Yep, it's
Yeah, I can see that.
Okay. Okay, so I wanted to say a bit about reporting standards and why they are useful and what we have been suggesting to use. So it's a bit of a different talk from the others earlier today, where you learned a lot about methods. This is more about reporting. Get this started. So I think we have a big problem with working in environments that the observations we are making are just points in a large area and at very few time points as well. And the environment is complex and changes all the time. We have spatial variation. Variation over time. Laura showed some time-dependent concentrations in London just in the last talk, and there are lots of environmental conditions that will affect what we are observing, that we should also record these factors that could have an influence on our measures of interest. We have a huge diversity of microorganisms, of course. That means if you're taking a small sample, we will be missing rare members of the community with some probability. We will almost always capture the ones that are more abundant, but we will miss some rare bacteria, potentially ones with resistance genes. There are lots of different resistant genes, thousands of them, and other genes that are resistant genes, but provide resistance as well. And there's tolerance and persistence and other things as well. And it all evolves. So we have also a complex mixture of potentially selective chemicals, not only antibiotics, but also disinfectants and metals and other things that could be selective. So it's very complex system to study. And we, of course, can't sample everywhere and all the time and measure everything. So we are ending up with pieces. And the difficulty is to bring these piecemeal observations together to come to some conclusions that are reliable. So we want to, have reliable large-scale trends and transmission pathways. We also want to understand locally what's happening, for example, if selection happens or not. So there are some solutions to that. One solution to bring different studies together and aggregate them are systematic reviews and meta-analysis. So I'll talk a little bit about that because I think that's probably many of you will not be familiar with that. I'm not an expert in it myself, but I have been learning about it recently because I realized how important these things are. They have for some decades now been become the standard practice in what's called evidence-based medicine, but they're also now used in other fields of science, which is good. The Cochrane collaboration is sort of seen as a gold standard for procedures in systematic reviews and meta-analysis, and there are lots of tools and tutorials and standards and guidelines, statistical tools as well to do the meta-analysis. That's all available, so it can be used, but doesn't have to be expert enough to develop these tools, just expert enough to use them. Some of the benefits of doing a systematic review or meta-analysis is that you can identify conflicting evidence and try to resolve that, or identify common trends or patterns. You come up with more general and robust conclusions that are not too dependent on the peculiar aspects of an individual study. And from pooling results, you can get a higher power in the sense of statistical power. Another solution would be coordination of sampling and measuring across different projects. This is something we should really be doing, but it is not easy to do. It's even difficult enough to coordinate within a project, let alone a cross project, but we really should be doing this. And using a common methodology or cross-validated methodology, which is in fact one of the tasks that we have in our program coordination team. Mathematical modeling can help somewhat to make connections between different studies at different scales, for example, connecting laboratory studies with mesocosm studies and field measurements. This can help, but mathematical modeling isn't going to rescue any bad data, but it might help identify when data are inconsistent with other data. But it can't, if the data aren't good, then modeling can't fix that, or statistics can't fix that. So a little bit about systematic reviews. I hope that is something new to you, so you can learn a little bit about this. Difference to normal reviews is that they are meant to be objective by using predefined criteria for selecting papers to review and then reviewing all of them that fit the criteria, and also using predefined criteria for evaluating the quality of the papers. So really analyzing the quality of publications. That is an eye-opener, I think, for anyone who's done that. In principle, the idea is that you have two different researchers that independently select and review papers, and if there is disagreement between them, a third one is going to moderate this. You can publish the protocol for this reviewing process before you're doing the review, which is a good thing to do. It will ensure that criteria are set up before you actually do the work. So that's recommended to actually publish the reviewing protocol. Normal reviews that we've all, I guess, have written are biased and subjective. There's no insurance that you screen all the papers for inclusion. It's maybe the ones you remember for one or other reason. And you're not using official criteria for selection, just citing papers. Often without properly evaluating their quality. And we all know quality varies a lot. Other benefits are that learning to critically evaluate published work, one will hopefully improve one's own work from the mistakes of others. So that should also be useful. Coming to meta-analysis, which can follow a systematic review, but adds to the systematic review that you actually extract data from different publications and work on them. So it consists of pooling data from several studies, if that is possible, and not always is possible. For example, pooling risk ratios or odds ratios from many small studies that are underpowered, statistically not enough power to detect any effects as significant, and get more power from the pooling and more robust results. Not always possible to do a meta-analysis if the studies are too different in methodology. It can't be done. There's too much heterogeneity. Some heterogeneity, however, will probably always be present. So you can deal with that to some extent with using subgroups or random effect models rather than fixed effect models. One example I wanted to show that's very relevant to antimicrobial resistance, and a good example, I think, from Bell et al. 2014. And they have looked at the connection between consumption of antibiotics and resistance. And the pooled effect size, the odds ratio was 2.33 for a positive relationship between consumption and resistance. So more consumption means more resistance. An odds ratio of 1 would be no effect. An odds ratio above 1 would be a positive effect, and this one is sufficiently above 1 to be statistically significant. And showing that across many different studies, there is a clear relationship between consumption of antibiotics and the level of resistance. This forest plot is I'm only showing about half of that figure from the paper because it wouldn't fit on the slide and still be readable. As you can see, there's a lot of variation. The solid line in the middle is the odds ratio of 1, which is no effect. The dashed line is the level where it becomes statistically significant, that the odds ratio is higher than 1. And you can see different studies. Some have huge variation, like these here. Some have results with a negative relationship. Most of them are on the positive side. Some studies have a very low variation, and for that reason, in this pooled analysis, a high weight. This one here has the highest weight, I think. They've actually taken it out. Still doesn't actually change the odds ratio too much if you take that study out with the highest weight. There are some other studies with low variation and therefore higher weight in this analysis, and overall the odds ratio is 2.3 and statistically significant. So this is what you can do in a meta-analysis if you find enough paper that use a similar enough methodology to be pooled. Okay, now our colleagues in Israel, Nasreen Hassoun-Kir, Yoav Starpolt, and Michal Paul have wanted to do a meta-analysis of all studies comparing hospital and community wastewaters in terms of AMR. We helped a little bit in this, but mainly the work was done by Nasreen and Yoav as reviewing the paper, and Michal as the moderator if needed. They are all clinical microbiologists, infectious disease experts, so they have done a lot of systematic reviews in the past on more hospital-related studies, and were quite shocked by the heterogeneity of results and methods in environmental studies. So some of the main findings were that the reporting on sampling methods and wastewater treatment processes and statistical analysis were at high risk of bias. So there was very little information and different information available in different papers. So the reporting was really too poor to be useful for a meta-analysis, and the heterogeneity methods also made it impossible to do a meta-analysis. What we wanted to do, we couldn't do, so we ended up doing only the systematic review. That came out last year. And the frustration from this was that really reporting in these papers was not allowing us, and the differences in what they reported didn't allow us to do meta-analysis. So as a consequence, we decided, no, sorry, I wanted to show a few more results from this review to explain it a little bit better what I mean by heterogeneity in methods. So this is one example about vancomycin-resistant enterococci in wastewater, and just looking at the different ways in which the results were reported, you can see that you cannot really combine the data. One way of reporting the results was taking the log counts per volume, so an actual absolute abundance of the vancomycin-resistant enterococci. Another common one was the number of positive samples out of all samples. Now that's a very different way of reporting this, and depends a lot on the volume of the sample. You know, the larger your volume, the more likely you're going to detect something that's present only is very rare in the sample. And positive or negative is just about detecting whether there's at least one in there or not. So depending on sample volume, of course, sometimes divided by the number of sampling locations when there was no information given on the number of sampling locations. Not a very useful way of reporting things. Or percent VRE, not very clear what that means. So you see 4 or 5 different ways of reporting what the data, which makes it impossible to use in any meta-analysis. Another example, again, I've cut out about half of the table because there wasn't enough space on the slide, otherwise you couldn't read anything. So this is the risk of bias analysis here for different categories, sampling comparability and analysis. For many different studies, you can see that if you look down columns, you can see that outcome units are quite often a problem. Statistical analysis quite often a problem. If you look sideways, there are some studies that have more green and others more red. So there's lots of variation. U means unclear, and blank means not applicable. So lots of variation between different studies. So as a consequence of this, we decided to come up with reporting standards. And in order to draw up reporting standards, we gathered input from a number of different researchers. In total, we had at the end 21 experts giving input into what was new to me, the multi-step modified Delphi consensus procedure, which is basically a mechanism to ensure that there is agreement between all experts on each particular item. It wasn't too difficult, but anyway, the procedure might have hopefully also worked with if there had been more differences of opinion. We are now calling this reporting standard Embrace Waters. It's an acronym that is difficult to remember for what it actually stands for, reporting antimicrobial resistance in waters. So Embrace Waters, that has come out a few weeks ago in One Health. Lots of authors, because all 21 experts are on that paper. Thanks all of them for contributing. And I just wanted to spend some time going through our recommendations on reporting. Some of this will be obvious, some will be less obvious. So I spend more time, I guess, on those which are less obvious. This is, there are 21 in total, so I put it on 2 slides. Title, abstract, and background. This is kind of the normal things, what you would expect. Describe the environmental compartment and resistance study. So already in the title, you should be clear about what system have you studied and what exactly have you looked for. A recommendation of a structured summary. And the background you describe, well, the background and the rationale of the study, that's not surprising to anyone who's written the paper. Now, in terms of the methods, so this is about planned locations, so locations that were planned before starting the study or before taking the samples. You should report on predefined sampling locations, give a rationale for why you've chosen particular locations. And then describe the sample types in each location. Was it a water sample? Was it a sediment sample? Was it some other kind of sample? Be very clear about that. And the technique employed to sample, like, you know, a Laura's bucket grab sampling, or the passive sampling that she described, totally different results, or continuous composite samplers, you know, different methods of sampling will give you different results. So it's got to be very clearly explained how you took the samples, what equipment you use for sampling, and the volumes you sampled, because that is important to report the volumes, because a large volume is more likely to capture the heterogeneity of the environmental system. And then the sample processing for each sample type, and whether you took any steps on site to preserve the sample, like cooling or not, and how long did it take to transport to the lab, and all these things that can have an effect on the results need to be clearly reported. Source characterization, that's the point we had probably most discussions on, especially with the reviewers. Two different cases here. If there's a point source, there's no point source. So if there's a point source, such as a wastewater treatment plant effluent, or another inlet with some material, or from a farm, if you have a point source, you need to describe the point source as much as you can and the characteristics of the point source. And if you don't have a point source, you should describe the characteristics of the watershed from which the runoff enters the river, for example. So this is important, and I understand not always easy, but it is worth the effort of trying to find out exactly what is this wastewater treatment plant doing, what capacity does it have, etc. What treatment process does it use, or what farmland, what livestock was potentially contaminating the water. Then coming to the microbiological methods, describe the methods used to detect bacteria, how resistance was assessed, was it phenotypic, was it sequencing, or both, and the statistical analysis and analysis pipeline, what you plan to do, and sample number calculation is recommended as well. Now, coming to the results, you should report the actual locations sampled with GPS coordinates, so be precise and give the precise location, but also the kind of location. What is this? Is this a bridge, or is it the riverbank? All these things that influence the way you sample and what you sample. Reporting the season and dates and frequency of sampling. Surprisingly, that's not always reported, the dates or the season or any kind of idea of what the conditions were like at the time of sampling. And importantly, if you're taking a sample from the river, it doesn't matter so much what the weather is right at the time to take the sample, but what the weather was like in the previous days leading up to the sample. And what you take out of your river has gotten into the river before, and whether there was a rain yesterday that washed stuff into the river or not will have an effect. So you need to describe the weather conditions leading up to the sampling, depending on how long back the effect might be. You should generally measure and report water quality parameters and any other metadata, and report all these results per location. Any very important to avoid bias, include any negative results. Report everything sampled and measured. The units of analysis should ideally be concentration units and not absence, presence, or something like that, and have confidence intervals or error bars of some sort. Describe statistical analysis again. That is not surprising, I hope, to anyone. And discussion again, discuss findings in context of existing evidence, compare how what you found is consistent or inconsistent with other studies, and importantly, be clear about the limitations of your study. Okay, so that's 21 recommendations with some sub-points here, so a little bit more maybe than 21. And I wanted to show some examples, more or less randomly, not systematically removed, more randomly picked from the literature. I give you a little bit of time to read this now, because I don't want to read it out. Okay, I think I'll then in the next one, I can give you some time to read it. Okay, so I guess you can see that within about the same number of words, there's a lot more detailed information on the right-hand example, despite the fact that it is a more complicated thing to coordinate 10 different countries and 16 different treatment plants. It seems like very well organized sampling campaign and clearly described. Whereas here there aren't many samples sometimes. There is quite some description about the rivers and why these are sampled and so on, but it is quite unclear and a bit unsystematic the way this was sampled. What I also liked is that they were actually clear about taking the samples 10 times downstream from the effluent, 10 times the width of the river. Now, actually, this is something that Laura already mentioned, the fact that rivers, if the wider they are, the less mixed they may be, and the longer it takes for them to become mixed. And actually, one advantage of being now in a team of people including a number of hydrologists, that I've actually learned something very useful from my hydrologists. There's a rule of thumb, but this is only a rule of thumb for the mixing length. It depends on the width of the river. So the wider the river, the longer it takes for an influent point source to be mixed into the river. It also depends on the depth. So the deeper river makes it easier to mix laterally. So a wide, shallow river mixes least, and a more narrow, deeper river mixes more rapidly over a shorter distance. So you can use this to decide how far down from a point source should you take a sample, where you can expect the sample to be representative, or the grab sample to be representative of what's in the river. So very useful information I learned from Josh Larson from my team. Two more examples of planning sampling sites that I liked, because they were quite clear and clearly explained. One example here, showing one wastewater treatment plant and upstream and downstream sampling sites dotted along here at quite frequent, quite closely spaced. Also including flow measurements. So having some idea of how much discharge from wastewater treatment plant compared to the river. And you can see in this case, the river is quite small. So no more than 5 times the volume of water, the discharge than from the treatment plant, and sometimes only twice. So the dilution of the effluent will be very small. A point the other paper is also making here with the dilution factors, this is very nice, but means that you also have to know the discharge, so have some measure of flow to be able to work out these dilution factors. But I do think this is really useful. And here you can see sampling down the river where they have different sampling points after the point source. And things change, of course. There is quite a rapid change for the first few kilometers, and then not too much happens after that. Once you know this, you can plan your sampling better to get the right kind of distances from the point source to observe where things actually change. I think both of these examples are quite good ways of planning the sampling locations and reporting them, especially the fact that they used flow measurements, and for that reason we're able to work out the dilution of any point source. So to finish, I wanted to plead with everyone, including my own team, that we should be agreeing on these reporting standards for our own work. There may well be a need for modifying these standards or improving them, and I'm sure we will all be happy to improve these reporting standards based on any input or comments you may have. The idea is to have a kind of web page for updates of this. We haven't done that yet, but we should really be doing that. So if you do have any comments or suggestions for improvements, do get in touch. It would be great if you could agree on a core set of things to measure in all projects that we can compare across projects, like, for example, measuring absolute concentrations of E. coli as a sentinel organisms or an E. coli specific gene, to quantify bacteria, quantify genes, quantify chemicals, and water quality parameters sort of for environmental conditions. What's the oxygen concentration? What's the pH, salinity, all of these things. Can we agree on a common methodology? That's the question mark here. I hope that we can agree on some core common methodology and allow some variation, of course, for things that are project specific, where there will be different methods used or different methods tried or developed, of course, but that we have a common core of methods that we can use for for combining results across projects, and where we do use different methods, that we are aiming to cross-validate them. Yeah, I think I want to have enough time for discussion of these points. So one of our program coordination team tasks is in fact the cross-validation. It's one of my tasks, including organizing these workshops, which I more and more realize have been extremely useful so far, and we'll continue doing those. Ideally, we would do something like the paper that Laura mentioned from Diane Agar's group on harmonizing methods across different groups. I think that would be useful to do if we can, but at least have some cross-validation of our methods. Yeah, the paper that Laura mentioned comes from this consortium called HERD. Yeah, I think that was all I wanted to say. So we have some time for discussion of that, or comments or questions or anything. It would be great if you could unmute yourself for comments. Otherwise, you should put them in the chat. I'm not very good at reading the chat when I'm having my screen shared, so it might be good if someone else reads out from the chat if there are any questions. Please go ahead.
Yeah, so shocking and yeah, I mean, I'm responsible for a lot of of these variations. One of the issues is I've noticed a huge amount of diversity in the way in which people express frequency or prevalence, and this idea of also sort of volumetric, versus actual prevalence. And I don't know whether you looked into that, because when you're looking at, I always used to have this rouse with people when you're looking at risk. So at the bottom line of all of these studies, isn't it, is that we're trying to consider risk, exposure risks, and so if we're looking at exposure risk to human health, that's one way to look at it, and the other one is environmental health, and I guess this is all another kind of set of really difficult concepts, because those two are really different. But when you're looking at actual sort of volumes of bacteria or chemicals in a river, and you express it as a relative value. So you sort of normalize it against the number of bacteria, which is a way of standardizing between studies. You're not necessarily expressing what the risk is to a human if they gulp in 50 mils of water while they're sort of practicing swimming. So, what's your? I mean, this. I know this is kind of a little bit off the center, but I just wanted to know what your thoughts were on that, because I guess that you can just do both and then have the relative one, which is normalized against the number of bacteria in a sample, because you're looking at the frequency of occurrence of ARGs, but at the same time, you want to know if there's if somebody swallows this amount of water, that's how risk is generally estimated, isn't it? And
Yeah.
And this sort of comes, yeah, sorry, I'll let you answer.
Yeah, that I'm glad you're making this point. This is really important. The actual effect depends on absolute concentrations, whether that's infection risk, it's the dose of coronavirus or whatever you're getting. So the relative percentage of coronavirus in a wastewater sample doesn't matter. It's the total. It's a concentration that matters, and the concentration and the volume also matters, because if you have a large volume with a large concentration diluted with another volume further down the river, that's going to affect the concentration downstream. So it's a combination of considering what actually matters is always the actual concentration, so amount per volume. And that is also what we always use in mathematical models. We have to operate with that. Or, even chemical kinetics, everything is really dependent on absolute concentrations. But the concentration, of course, have something to do with volume as well, because it's a question of load. How much do we get out of the treatment plant matters if it comes to concentration in the river. So it's a concentration in the treatment plant effluent, but also the volume coming out, so the load into the river. And our idea is, it's difficult to quantify everything. So we are hoping that by quantifying E. coli, doing counts on plates, and also including E. coli genes in qPCR, and including E. coli, of course, in metagenomes, that we have one thing that can turn all the relative measures into absolute measures. How well this is going to work, I don't know yet. I do hope it's going to work, and that will be our hope for turning all the relative measures, which will be, relative to maybe 16S or something, and turn that into absolute measures.
Yeah, and I think that the other issue is the metagenomics is, first of all, there's different pipelines. So there's all of that, which huge variability, and the cutoff level for similarity and so on. And but on sort of prior to that is the sort of sampling depth, and then how it's expressed, sort of the per number of reads or so on. So I'm really eager for us to sort of sit down and have a big workshop on that as well, because that's another one that all different people normalize in different ways. So we work with Chris Quince, and he normalizes in a different way to other people, and this is something that is crucial if we're comparing like with like and looking at similar risks. But it's quite difficult to persuade a bioinformatician. Once they've got their methods and their pipelines, they're very dedicated to them. And, that's another issue, that, we have to be able to take ownership of these things and make sure that we are comparing the same thing,
Yeah, but I think to a large extent, it boils down to sort of common sense and being aware that there are different pipelines that will produce different outcomes, the sensible thing to do is actually run
Compare.
different pipelines.
Yeah.
And do
Yeah.
the conclusions actually hold? If I change the way I analyze the data, do I get the same
Yeah.
qualitative conclusions or not? I think every careful scientist who's kind of proud of the work they are producing will do that and, you know, check, you know, it's experimentally, you know, using positive and negative controls and being careful. Laura mentioned something that actually we haven't done, you know, bringing clean water into the field. This blank sampling thing is something I have to say we have not considered.
No. Yeah. Same here.
Learning what best practice and being careful and accurate with your note-taking and reporting, that's what it boils down to, really.
Yeah. So with India, we're swapping. So we're swapping sequencing. So we're doing some sequencing, they're doing some, and then the sequences swap, and they do their pipelines, we do ours, and then we bring them back to compare. So that we're trying to do that across qPCR and at least for the other, you know, things that we're doing. But the sampling is difficult to control, and I know that Laura also has these issues with transportation, and this is another problem because if we want to swap samples between labs, this is also really good practice. In the past we've used dry shippers and things like that, which I think, you know, we need a workshop on sampling. Yeah, but I think a very important point, and many important things, but I'm sure other people have got lots of queries they want to raise. Or maybe not.
I could say something if anybody else.
Sure.
Thank you. That was really interesting. And it made me think about a project I was involved in a couple of years ago. So I tried my skills at modeling. So I swapped and tried to gather data from the literature to test whether published in models actually worked when you use real environmental data. And it really opened my eyes as to the types of data that are reported and the quality. And I think when you're coming at it from like perhaps a chemistry or a wet lab perspective, you don't always think about how the data is going to be used in the long term and what somebody else might need if you're going to say model it or to try and use it again in a different source. So I think coming at it from my experimental perspective really sort of opened my eyes as to what is needed. But I think the point I'm trying to make is we have a variety of skills in our program that really cross the disciplinary boundaries in terms of what we need. And I think if we can work together and come up with these reporting standards, then we'll be able to link really well because we'll be able to establish what people with a modeling background need in terms of data and combine that with what we need to generate from a sample perspective and the types of water quality parameters, for example, that we need to measure, and to create this like comprehensive set of ideal reporting scenarios, I guess. So I think we're in a really good place to do it, and I definitely think there's a need for it. So it's not really making any important point. It was more echoing, I guess, what's been said. But yeah.
Yeah, thank you, Laura. Has anyone listening to these reporting recommendations I've gone through briefly had the feeling that there's something completely missing or something completely wrong? Just to get some kind of quick feedback on those. Try to see whether there's anything in the chat. Do feel free to put things in the chat as well. I'll try to read this as well.
I mean, there's always that thing about season, and this is coming up a lot in India because there's such big differences between seasons, and the chemist who's in our on the Indian side in our group, Zia, who's also in Selecta. I think he's in yours, isn't he, Laura? He thinks that the monsoon doesn't have a dramatic effect. He thinks that because we measured during the monsoon and we found the concentrations drop dramatically. So this is another issue is whether, the general consensus, as pointed out in several of the talks, is the volume of water is a beneficial diluting effect. So this is the argument with wastewater treatment plants and CSOs and shit in the river, basically, is that you've got a lot of water coming and it dilutes everything. And I think that this isn't always the case, because it's increasing runoff from the land and pollution. So it's going to be really interesting to see how that impacts, because that is the consensus in India quite a lot. So there's yeah.
Liz, I think a little bit confusion is there, because I mentioned when you try to collect sample from the industrial premises, obviously you will not see the variation in different season, because industry, they are not going to change the production based on this rainy season or winter season. So whenever you collect the sample from the outlet of the industry, you are not going to see much difference. But obviously, if you try to check their abundance in the receiving water bodies, it is quite obvious. Whenever you get dilution, you will see the dilution effect. But if you take the sample from the outlet of the industry, and especially the CETP, most of the common effluent treatment plants, they get the effluent directly through the covered drain. So they are not open drain. So if you have pipe drain, and this pipe will actually be bringing all the effluent from the industry. So if you take the sample from the inlet of CETP, there also you'll not find much variation in different seasons. But if you go to the final receiving water bodies, definitely you will see the difference, because the normal rainwater, stormwater, as well as the treated effluent, they will go to the receiving water bodies. And it is quite obvious in rainy season, you'll see the dilution. So I think perspective is different. If you just choose the sampling site or sample collection points, then definitely you will see different kind of phenomena. And it is quite prominent that if you take the sample directly from the industrial outlet, the seasonal variation will not be that prominent.
Yeah, no, I think that wasn't the point I was trying to make. Sorry. It was more that the anticipation was that in the monsoon, and this was I got from the presentation that was in the part of the workshop that was organized for AMR Share, it is that the monsoon won't necessarily dilute. It'll actually make the situation worse, that you'll get higher levels. And this is a sort of a priori supposition that, and then several people showed that there was dramatically less antibiotic. And I thought you felt suspicious of that. That was what I was saying.
Yeah, David has raised his hand.
Yeah,
I was going to make a comment about this because we've looked at the monsoon in a number of different places, including India. And what happens during the monsoon, and some of this work is with Sia, is that during the monsoon, you do get dilution, but you get a huge amount of resuspension of sediments, which, so the effects of concentration is really somewhat unpredictable. What you definitely get during the monsoon is a much higher level of mass loading down the river, and that just is common sense. And it depends also on the time within the monsoon you are, because early in the monsoon, you get a huge amount of sediment resuspension, but after you've got scouring, you end up with the concentrations becoming more dilute as the sediments have been scoured. So it's it's not really completely black and white, because we've seen places where in the monsoon you actually do get consequential dilution, but in other sites the concentrations actually go up.
Yeah,
and it's not 100% consistent.
Yeah, but that was the point that I think that I was making, that Zia had made those observations, and it was the opposite of what I've heard other scientists say, and the sort of, you know, the consensus opinion in the UK water industry is that, you know, heavy rainfall dilutes everything, and that isn't necessarily the case. And so
yeah, and that's true, and it's because we don't have, our sediments are not nearly as polluted as other parts of the world where there isn't a lot of wastewater treatment or consistent wastewater treatment. So it's a matter of the nature of the sediments that get resuspended that affects what you get during the monsoon. And so in the UK it happens, but you generally do get dilution, but it's just because we're not respending the same types of things as you are in a place like India or where we work a lot in Latin America. So,
but there are a lot of bacteria in the sediment. That's the thing. Not to be ignored.
Absolutely.
One thing that I heard anecdotally from some of my team members is that the industry knows that monsoon is going to dilute, so they are dumping much more when there is rain, because then it won't be discovered. So I think that adds another complication to this important question. I'm conscious of time, and many people will probably have to leave now. So I want to take the opportunity to thank everyone for attending, and the speakers for clear presentations, apart from my own, of course. And we're going to do more workshops because there's a real need for addressing other topics as well. And the few things we have already discussed, we probably need to go into some more depth with some of these as well. So if you have any suggestions for further topics, or volunteer to give some presentations, you don't have to be the world expert to give presentations on a particular topic. It's more about getting a discussion and awareness going. So I'd be very happy to get any volunteers contacting me, or suggestions or requests for topics. So thank you everyone for your contributions. I am trying to turn these recordings into YouTube videos. That might take some time, and I also try to upload the talks on our website. Again, I'll have to see how easy this is going to be, but I will try to make these things available. I'm actually trying to hire someone to do the video editing because I don't have enough time to do that. So we'll help to get this out at the beginning of next year. So thank you all very much, and I guess maybe trying to wish you a good break over Christmas and all that. So thank you all, and see you next year. Goodbye.
Yeah, thanks very much, Jan, for all your efforts and hard work, and to the speakers today. It was fantastic talks, really, really useful. I think everyone fully appreciated it, and gives us a great opportunity to really exchange ideas.
Yeah, thank you all.